Good afternoon, everyone. Join fast. I'm waiting for you all. I hope everyone is joining for this part 2 session. Okay, so I will start here. So today we are discussing about the spring, potential energy of the spring. We did it in the last period or in the last session. So in this session we are doing energy consideration for a spring block system. So here I already drew the diagram on the board. Here we have a rigid support, and normally I placed a block of mass M to the spring. So that is the position A. Then afterwards I pulled back. Okay, that means I stretched that spring at position B. There is a displacement from the mean position. Okay, this is the mean position and the displacement is positive here, and in this third case I applied the force on the block of mass M towards the rigid support, so it is get contracted and that it is also displaced from the mean position X, and that displacement is negative. In the last session we discussed here, whenever we are applying force, okay, either we are elongating or we are compressing the spring, in both the cases there should be a restoring force, okay, and that restoring force always acting in the opposite direction of the applied force. Okay, so we did in the last class the F is equal to minus F is equal to X, and also we discussed about the Hooke's law and the potential energy of the spring. Okay, so today we are deriving the energy conservations for the spring in these two cases. Here the first is nothing but the spring is at we kept at the main position, and this is A is nothing but here mean position. Okay, so we are displacing this body of block M through distance dx against the restoring force. Okay, in the second case here I applied a force. Okay, here I took back, this is a force, so restoring force is acting in the opposite direction because it always wants to regain its original length. Okay, so the restoring force is acting in the opposite direction. There should be a small amount of work done takes place, okay, to increase the length of the spring. Suppose here total displacement from the mean position B, mean position from A to B, this total distance is X, but we are taking a small work done and the displacement is also small here. Okay, so work done over here, we can write work done dW is equal to minus F into dx, force into displacement. At the beginning of this session, when it's the last session, I told you work done is nothing but what? Force into displacement, and this is minus F into dx. And this force is nothing but what? Yes, in last session we did, that is minus kx into what? Dx. Okay, F is nothing but here kx, and kx into dx we are taking. Now here if we want to calculate the total work done, so we are displacing from mean to max position, that is x, so we can integrate on both the side 0 to w. 0 to w here is equal to integration of 0 to x from mean to maximum position x. We can take a magnitude over here kx into dx. Okay, just we integrated here, and we know that 0 to w work done is nothing but here w, 0 to w upper minus lower, we will get total work done w, and here if we are taking k as a constant 0 to x, then inside this integration x dx will remain. So if you take the integration of x dx is nothing but x square by 2. This we can write as a x square by 2, and limits are 0 to x. Okay, and then you will get here kx square by 2 upper minus lower limit. Okay, we will get this as a work done. Okay, work done is also known as what? Potential energy in the spring. So here potential energy is equal to half kx square. This potential energy at point B. We can mention this potential energy at point B. If you want to plot a graph for this, then you can take here displacement x and you can take a force F. Okay, as applying force is increasing, then displacement from the mean position is also increases, and you will get this kind of graph. Suppose if I am taking this as a P and Q, and we know that if force is changing, then work is also changing. Okay, so we know that work done due to changing force, area under the graph. So if you want to prove this here, work done is nothing but what? Half area under the graph. So I can write here area under the graph. Okay, so area under the graph, this is a right angle triangle. So half base OQ into, this is height. Height is nothing but here PQ. So half OQ is nothing but displacement and PQ is nothing but force. And you can substitute force F is equal to Kx. So we can write here half x into Kx, that is equal to half Kx square. This is nothing but what? Your work done at point P. Okay, hope you understood the work done at point B. Okay, I discussed only one question, so you can take a screenshot or you can note it down. So I will go for the next position, that is C. Okay, note it down or you can take a screenshot. Okay, here I did with a graphical method also. I hope you took the screenshot. Then we will go for the point C. Okay, so here if we leave the body at point B after stretching, if we leave the mass of block at point B, then it is what? Started accelerating, means it acquires the kinetic energy, and in that case potential energy will become 0. Means it will come to A and it is what? Started moving to and fro. So in that case potential energy possessed by this body is 0 and maximum kinetic energy when we release that block from B. Okay, now at point C what will happen? Check. Okay, again I will show you here. When we take this block and whenever we are applying force on this block, okay, so my force, application of the force in this direction, and now restoring force is acting in the opposite direction. Now here the body is get displaced from the mean position, and this displacement I will take it as a minus x. In previous case I took as a right hand side, point B from the mean is positive. Now I compressed by using the force, that spring is compressed. Now that distance, the displacement is nothing but here minus x. So in that case C is nothing but in that case whenever it is accelerating, in that case it is showing maximum kinetic energy, and whenever it is at a rest condition, then it shows the maximum potential energy. Okay, so here now at point C, I stretched and I compressed and I hold it. Okay, I didn't left that mass of block. So whenever you compress that block and if you are holding, in that case it shows the maximum potential energy. Okay, in that case at point C, potential energy is what? Maximum, and this potential energy is nothing but half K into minus x whole bracket square. Okay, this is a spring potential energy, and here we can write it as half kx square. This is nothing but potential energy. So in the last case also we got the potential energy at the extreme position is half kx square, and here also we can got half kx square. Okay, so from this from here we can say that the total kinetic energy is get converted into potential energy. So we can say that total energy. So what do you mean by total energy? Here if we write total, total energy of any system is nothing but what? Kinetic energy plus potential energy. So at point B, the potential, we got the energy, total energy as a half kx square, and here also kinetic energy at point C is 0. So kinetic energy is equal to 0 at point C, and at point B we got potential energy is equal to half kx square, and in that case also kinetic energy is 0. So total energy for both the systems is nothing but half kx square. So here total energy of the system is remains conserved, or here we can say that total energy at all the points will remains same. Okay, so this is nothing but what? Your energy conservation in the spring. Okay, for a block system. And if they ask the graph for this, then you can draw the graph. So here there is a displacement. Okay, and here we have a total energy, and this vertical axis represent the energy E. Okay, so we can take our mean position A. This is B, as we took it as a positive displacement, and this is nothing but what? C. Okay, that is the displacement at the negative. So here whenever we are elongated the block from the mean position, so in that case your potential energy is what? Get increases, and slowly kinetic energy is what? Started decreasing. Can you getting this? Okay, so now again if we are at point C, then again potential energy is increases. Okay, and kinetic energy is what? Here again decreasing from maximum to minimum. Okay, so green color part indicates the potential energy, and here black color indicates that the kinetic energy. Okay, so this is what the graph for the energy conservation in the spring of block system. I hope you understood this derivation, very important derivation from the exam point of view. Okay, so take a screenshot of this. You can take a screenshot of this. So total energy is nothing but a sum of potential energy and kinetic energy. So we have to discuss one more system for energy conservation. Okay, there also we have to discuss about the different energy situations, and we have to show that the system will remain conserved. Okay, along with the graph. So I hope everyone took a screenshot of this. Then now next point, that is illustration of law of conservation of a system. So how here we shown the system, means spring system energy levels at each different point are remain same. Energy, spring energies get conserved. So similarly here we are showing initially a body. Suppose this is a surface and here we have a body A. So its height from the ground is nothing but h. So whenever the body is at A, okay, at certain height we kept that body, and in that case that body shows the maximum potential energy. Okay, so here we can say that kinetic energy and potential energy for the system A we have to calculate, and once we get the kinetic energy and potential energy, then we can calculate the total energy for that body. Okay, so here at point A, so I will write here at point A. Okay, kinetic energy is equal to 0 and potential energy is nothing but mgh, because it is raised at certain height. So whenever we are taking object and keeping at certain height, then it shows the maximum potential energy mgh. So here the total energy of the system for A is nothing but kinetic energy plus potential energy is nothing but mgh, because kinetic energy is equal to 0 here. Now body allowed to fall freely and it reaches to point B with velocity v. Suppose I drop this body from certain height and it reaches at point B. Okay, from A to B it covers the distance x. Okay, and now here this body B from the ground, how much is the height from the ground? Its height will come h minus x, total height minus this covered distance is x. So from the ground to body up to point B, h minus x. Okay, so now we can calculate the kinetic energy and potential energy at point B. Okay, so at point B, potential energy, okay, potential energy is how much? Can anyone guess? Okay, if not, then we can discuss first kinetic. So as that body is traveling from A to B and it covers a distance x with certain velocity v, then we can use the kinematic equation v square minus u square is equal to twice of as. So initial velocity becomes 0, so v square is equal to twice of as u is equal to 0. Now here acceleration, a is nothing but here g. Okay, as body is freely falling from top to down, so here a is nothing but g and s is nothing but here x. Okay, so we can write v square is equal to twice g x. Okay, this is nothing but v square, v square is equal to 2g into x. Then what is the kinetic energy over here at point B? Kinetic energy is nothing but half mv square. So half m v square, I will substitute this value 2 into g into x. So 2 get cancelled and I will get mgx. This is nothing but kinetic energy at point B. Now I am interested to calculate the potential energy from at point B. So here from height of the body at a B above the ground, okay, that is nothing but h minus x, and potential energy at point B, potential energy at point B is nothing but mg, and this height is how much? H minus x. So simplify this bracket, mgh minus mgx. Okay, so total energy at point B is nothing but kinetic energy plus potential energy. So kinetic energy is how much here? mgx, and potential energy is mgh minus mgx. So mgx minus mgx is get cancelled and mgh is the total energy at point B. Okay, so if you check total energy at point A and at point B are nothing but mgh. Okay, now our body reaches at point C here. Okay, now it reaches at point C or strikes on the ground at point C. So in that case also it is traveling with certain velocity. So here straight away we can observe we can write here at point C potential energy becomes 0 and kinetic energy is nothing but half mv square. But the problem is that now here again the body is traveling with certain velocity and we can write here v square minus u square is equal to twice as. Again u is equal to 0. So 2 v square is equal to 2g into how much? We can write height is how much here? Height is nothing but here we are taking it as the h. Okay, so it travels the total distance h. So here we can write it as 2gh. So here substitute half m v square is nothing but 2gs, 2gh, 2 and 2 get cancelled, mgh is nothing but kinetic energy. Okay, and if you calculate total energy at point C, that is kinetic plus potential energy, so kinetic energy only present, so that is nothing but mgh. So this is nothing but the total energies at 3 different points. Okay, and if you observe all these 3 different points, you can get the total energy is nothing but mgh. From this we can conclude here the total energy at point A, B and C is equal to mgh. That means energy remains conserved at all the 3 points. Okay, I hope you understood this. So take a screenshot of this. You can take the screenshot of this. Okay, after that we have to draw total energy graph. Okay, everyone understood this? Then we can draw the graph for total energy. Okay, so here in all the cases, as potential increases, kinetic energy decreases. As kinetic energy increases, then potential energies get decreases. So here both are interrelated with each other, and if we draw a graph, on x-axis we have a displacement and here we have a energy E. Okay, and this gives the total energy, addition of potential energy and kinetic energy. As here kinetic energy decreases, as the kinetic energy decreases, then potential energy is what? Increases. Okay, so this is nothing but what? Total energy graph for energy variation with positions for a body under freely fall. Okay, so mostly this question comes for total 3 marks. So graph they allotted total 1 mark over here. Okay, I hope you understood up to here. Now we are going towards or moving towards the collision. Okay, collision means what? Two bodies are colliding on each other. Okay, so whenever there is a collision means one body means both the bodies are moving, or one body is moving and another body is at rest, or vice versa. So they are striking on each other, and after striking they both are moving, or sometimes one body will become at rest and another is what? Moving in the same direction or maybe in the different directions. Okay, so here collision is nothing but the two bodies are striking on each other. Collisions are of two types, that is elastic collision and inelastic collision. Okay, so here what I will do, I will make two different columns and then I will explain elastic collision. Okay, so elastic collision, and here we have inelastic collision. Okay. So now very first point. So this is nothing but elastic collision is conserved. It is get conserved. That means here whatever the total energy is there. Okay. Total energy what remains conserved everywhere in a whatever points we are taking, everywhere that total energy is get conserved. And here also in inelastic collision total energy is also conserved. Okay. Then next point, kinetic energy is conserved in elastic collision. Kinetic energy is also conserved, and in second, kinetic energy is not conserved at elastic collision is not conserved here in elastic collision. Okay. So here total linear momentum P that is total linear momentum. Total linear momentum is also conserved. Okay, so can you guess about the inelastic collision? Here also total linear momentum is conserved. Total linear momentum is conserved. Very important. Then last point, here we can say that forces, okay, dissipative forces are not involved, and here dissipative forces are involved in the inelastic collision. Okay, so these are the differentiating points for elastic and inelastic collision. Okay, so only everywhere in both the cases total energy is conserved. Kinetic energy is conserved only in elastic collision, and it is not conserved in the inelastic collision. Then total linear momentum, that is P, is conserved in elastic collision, and it is not conserved, that is linear momentum is not conserved in elastic collision. Okay, so now even the dissipative forces are not involved, and here in case of inelastic collision dissipative forces are involved. Okay, so now we are discussing about the elastic collision in one dimension. Okay, getting everyone? So these are the some points are given for elastic and inelastic collision. Okay, now we are discussing about the elastic collision. Okay, in one dimension. Elastic collision in one dimension, 1D. Okay, so here we have two bodies, okay, having mass m1 and moving with velocity u1, initial velocity. Another body having mass m2 and it is moving with initial velocity v2. Okay, when they collide on each other, okay, when they collide on each other, okay, after collision they are what started, their masses will remain same, m1 and moving with velocity v1, and another mass of body m2 moving with final velocity v2. Okay, so this is nothing but what? Before collision. This is nothing but before collision. Okay, during collision, and this is after collision. Okay, so these are the three conditions we have. So here initially a body of mass m1 moving with velocity u1, then body of mass m2 moving with velocity u2. Then when they collide on each other, again after collision both the masses m1 and m2 are moving with final velocities v1 and v2. So from this we can say that since elastic collision where the total kinetic energy is conserved, then we can write it for the two different bodies. Okay, initial kinetic energy is equal to final kinetic energy. Initial kinetic energy half m1 u1 square and here half m2 u2 square, and final will become half m2 v1 m1 v1 square plus half m2 v2 square. Okay, so you can cancel it out half on both the sides. Okay, if you cancel it out, then you will get m1 u1 square plus m2 u2 square is equal to m1 v1 square plus m2 v2 square. We will get this equation. Everyone is getting this equation? Okay. Now interchange the terms, that means you can bring this m1 to this side and transpose this m2 to that side. So m1 u1 square minus m1 v1 square is equal to m2 v2 square minus m2 u2 square. Now take m1 common here, so u1 square minus v1 square is equal to, if I take m2 common, then I will get v2 square minus u2 square. Can you getting up to here? Okay. Can you getting up to here? So you can take this as a equation number 1. Okay. Now take a screenshot, as I have only one board. So I require the board again for the further derivation. Okay. I hope you are taking screenshot. Okay, and after that I will teach up to coefficient of restitution. Remaining derivation we can do it afterwards. Okay, so here we got, you can take this as equation number 1. Since this elastic collision where the linear momentums are also get conserved. So linear momentum is nothing but what? M into V or M into U. So linear momentums are conserved, that means initial linear momentum is equal to final linear momentum. Okay, so here m1 u1 plus m2 u2, this is initial momentum, and then final momentum, that is m2 v1, m1 v1 plus m2 v2. Can you getting? I just expanded this linear momentum ka formula over here. Okay, and then here again you can transpose the terms, m1 bring it over here, m2 you can transpose to that side. So m1 u1 minus m1 v1 is equal to m2 v2 minus m2 u2. So here you can take m1 common, u1 minus v1, and here m2 v2 minus u2. Okay, so this is what your equation number 2. Okay, I hope you are copying properly, you are making your notes according to me. Now these are the main 2 steps we did. Now we can divide this equation 2 to 1. Okay, divide equation 1 divided by 2. So 1 I have here, m1 u1 square minus v1 square is equal to m2 v2 square minus u2 square divided by m1 u1 minus v1 upon m2 v2 minus u2. Okay, so m1 m1 m2 m2 is get cancelled, and here after that you can write it down. This is nothing but expansion of a square minus b square, that is a plus b, a minus b. This identity I hope maybe you learn this in the 9th and 10th standard. We have a square minus b square is equal to a plus b into a minus b. Okay, so you can expand this. So here u1 minus v1 and u1 plus v1 upon u1 minus v1 is equal to v2 minus u2 and v2 plus u2 divided by we have v2 minus u2. Okay, so v2 minus u2 get cancelled, u1 minus v1 and u1 minus v1 get cancelled, and we are getting here u1 plus v1 equal to v2 plus u2. Okay, so I will transpose these terms over here. u1 plus v1 divided by, I can write v2 plus u2 is equal to, I will get it as a 1. Okay, or this we can write it as E. So E is nothing but coefficient of restitution, and this coefficient of restitution is defined as a ratio of relative velocity of a separation to relative velocity of an approach, that is called as what? Coefficient of restitution, that is denoted by letter E, small e, and always for elastic collision the value of coefficient of restitution is always 1. Okay, getting this up to here. So we can do the next part also. Okay, otherwise again you can forget these derivations. So we got this much. Maybe you have equation number 1 and 2 with you. Okay, with the help of that we are calculating expressions for v2 and v1. Okay, so in here we are taking case 1. So now what you can do, we got equation 1 and 2, no? Then we can take this as equation number v1 minus u1. Yeah, once you get this, okay, I hope everyone is took the screenshot. Now I will erase this part. Okay, now I got coefficient of restitution. So this only I will write it as u1 plus v1 is equal to v2 plus u2. So I can write u1 minus u2 is equal to v2 minus v1. This I will take it as a equation number 1, equation number 3. Okay, so after that we can discuss about the next case. Okay, to find out the velocity for after collision v1 and v2. So first we can find out the expression for v2, that is our case 1. We are finding out v2 here. Okay, so to find out v2 from equation number 3 we can obtain the value for v1. It's very important. If we want to calculate v2, then obtain the expression for v1. Okay, so after rearranging you will get v1 is equal to v2 minus u1 plus u2. Okay, this is the velocity equation we are getting. And now once you get this, okay, you can take this as a equation number 4. Now this 4 you can substitute in equation number 2. Okay, wherever there is a v1 you can substitute over here. So m1 u1 minus v1, no? So put the bracket v2 minus u1 plus u2 is equal to m2 v2 minus u2. Now transpose this negative sign inside the bracket. Okay, after transposing you will get the expression for v2. Okay, so we will get the expression for v2 is nothing but 2m1 u1 minus m1 u2 minus 2m1 u2 plus m2 u2 plus m2 u2 divided by, I am getting here m1 plus m2. Okay, m1 plus m2, getting up to here. Okay, and now here if we check properly, can we take here u2 common? Here check, this and this is same. So here only I can write the expression for v2, final expression we can write it as a 2m1u1, 2m1u1 minus, we can take, okay, you are not, you can take interchange the term, plus you can take u2 common, and inside this bracket you can write m2 minus m1 divided by, we can write it as a m1 plus m2, that is total mass. So this is nothing but what the velocity we got it for the second body having velocity v2. Now we want to calculate the velocity for v1, body m1, velocity is v1. As I told you, as we calculated velocity v2 by obtaining the expression v1. Okay. Now I want to calculate v1, that means I have to obtain the expression for v2. Okay. Now this is the second case. This is second case. Here we want to find out v1. Then from 3, with the help of equation 3, obtain the expression for v2. Okay. So v2 is nothing but u1 minus u2 minus v1, sorry, plus v1. Okay. So this is nothing but what your fifth equation. So now take fifth equation and substitute in equation number 2 again. Okay. So once you substitute in equation number 2, this is what equation number 5. 5 you can put it in 2. So m1 u1 minus v1 is equal to m2. v2 you can replace now. u2 minus u1 minus u2 plus v1 minus u2. Getting this? So this is nothing but what we are getting equation. Now simplify, multiply this m1 and m2 inside this bracket. Okay, check what are the terms are going to be cancelled. So after doing all the cancellation and all, I am getting the velocity v1 is equal to 2 m2 u2 plus u1 m1 minus m2 divided by, I will get it as m1 plus m2. This is nothing but velocity of a body 1 which is moving with velocity v1. Okay. So these are nothing, this is nothing but what the velocities. So now you can take different equations, means different cases, as both masses are same, where body 2 having initial velocity 0. Okay, like that you can make a different cases and find out the special expression for the special cases. I hope you understood the elastic collision over here. Okay. If you have any doubt, you can just message me in the comment box, so we can discuss about the mechanical power also. So this chapter is what get over. So mechanical power or any power is known as what? Rate of doing work. Okay, rate of doing work is nothing but what? Power. So we can write power P is nothing but work done by time. Okay. So we can write here power P is nothing but work done divided by time. Power we are measuring in terms of watt. Okay. Or we can write another unit, joule per second, as the work done is one kind of energy, and energy we are measuring in terms of joule, and time we are measuring in terms of second. So joule per second is also known as a 1 watt, and its dimensions are m1 L2 and t minus 3. Okay, so here, and unit is nothing but unit joule per second. And here if you take any mechanical device or any device, okay, and if we are calculating the efficiency, always remember efficiency of any ideal body is 100%. Okay, and efficiency is denoted by letter eta or some eta, and this is nothing but what? Output power, ratio of output power to the input power. This gives the efficiency of that device, and if you want to take percentage, then multiply on both the sides by 100. Okay, so you will get the efficiency in terms of percentage. Okay, I hope you understood this lecture. So if you have any doubt, before asking the doubts, you can check previous video also, and then if you have any queries, just message me. Okay, thank you, thanks a lot.